Because later on we'll be talking about conservation of momentum, we're obviously going to have to also think about changes in momentum. So let's talk a little bit about how momentum can change. Because momentum is a vector, we can change it in two different ways. You can either change its direction, like this, or you can change its magnitude, like something that stopped can go, or something that was going could stop. So we'll do two examples of this now. First is an object coming to rest. So let's say you have a teddy bear, it's nice and squishy, it falls with a velocity v, and after it lands, it kind of squishes down. So just before hitting the floor, the velocity is in the minus y direction. Therefore, the initial momentum can be written as p is equal to negative mv, because the velocity is in the negative y direction. Now we have the final momentum. Afterwards, you can see, again, you get p equals mv, but the velocity is 0, so the final momentum is 0. If we want to think about the change in momentum, we should take the final minus the initial, which is 0 minus negative mv, which gives you positive mv. So, interestingly, in this example, you notice that the change in the momentum is actually in the positive direction. And we have to think, should we expect that? And that makes sense because initially it was moving, this object was moving with a negative velocity, and then it becomes 0. That means it must have gained momentum. So it gained a momentum of mv. That makes sense. Let's do another example also of an object dropping. So let's say we have something like a red rubber ball. It drops, again, same as the teddy bear, with a velocity in the minus y direction, and therefore it has an initial momentum of m minus v, or minus mv, because it's moving in the negative y direction. But then after it bounces, it has a final momentum, which is now equal to mv, because it's moving in the positive velocity direction. The velocity is positive, and so therefore the final velocity is mv. Therefore, let's think about the change. We get delta p is equal to pf minus pi, and that gives us 2mv. And again, now when we have the rebound, we actually see that the momentum that was imparted to the ball is twice that as it was to the teddy that just landed. And this makes sense as well, because now you're not only you're imparting twice as much momentum because you completely changed its direction, and now it's moving off in with the same velocity, but in the exact opposite direction. So again, we have to think about the direction of the momentum in order to use change in momentum. If we had an object that was moving at an angle, you would do the change in momentum in both the x and the y directions separately, and then combine them in order to find the total momentum of the object afterwards. Before we leave, there's one more momentum type of concept that we want to touch on, and that's angular momentum. So if we have an object that's rotating around in a circle, it has some constant velocity that it's moving in that circular motion, and it has an angular velocity of omega. We could measure that momentum over time, but that momentum is constantly changing because it's moving around in a circle, and it's not really giving us that much information. So instead, what we can do is talk about the angular momentum L. And the angular momentum L is just r times mv. If you have a particle of mass m and it was moving with a velocity, a tangent velocity of v, which is basically equal r times the linear momentum. We'll come back to angular momentum in the next lecture for Wednesday when we talk about how these things can relate to force, and in this case, how angular momentum will be able to relate to torque.